I'm Dr. Elinor Martin, Assistant Professor at the University of Oklahoma's School of Meteorology, and today I'll be discussing the balance of the Earth's energy budget. The Earth's energy budget determines the globally average temperature of Earth, which governs whether we have a livable planet covered in beautiful plants and animals or a cold, barren landscape. The essence of the Earth's energy budget is the balance between incoming shortwave radiation from the sun and outgoing longwave radiation from the Earth itself. When the incoming and outgoing energy are in balance, then the Earth's average temperature stays constant. When one or more parts of the energy budget changes, an imbalance occurs, and then Earth's average temperature gets warmer or colder in response. The Earth's energy budget has many individual processes and interactions that contribute to the balance of the budget. Some of these processes are very influential, and some of these processes have a much smaller impact. Today, I'll be covering the processes that have the largest impact on the budget. Energy from the sun is emitted as shortwave radiation due to its high temperature. It takes just over 8 minutes for this energy to reach the Earth, and we experience this as a combination of visible light and radiant heat. First, let's think about the Earth's energy balance if there were no atmosphere. Bright surfaces like snow, ice, and desert sands reflect almost all the incoming solar radiation back into space. Dark surfaces, including forests and asphalt, absorb the radiation and hold on to it as heat. That's why deserts like the Sahara in Africa can fluctuate by as much as 70 degrees Fahrenheit from day to night, while parts of the Amazon basin in South America fluctuate by less than 10 degrees Fahrenheit. Over the whole globe, the amount of incoming solar energy that is reflected is about 30%. Energy from the Earth is emitted as long-wave radiation, as the Earth is much cooler than the sun. With no atmosphere, all of the long-wave radiation emitted by the Earth would pass directly back out to space. With no gases in the atmosphere, the Earth's surface temperature would be about 0 degrees Fahrenheit and probably couldn't support any life. Luckily, the Earth does have an atmosphere, so let's consider the energy balance of just the Earth and the atmosphere. Most of the gases that make up the atmosphere of the Earth are transparent to the incoming solar radiation and allow it to travel all the way to the surface of the Earth. One major exception is ozone, which absorbs the ultraviolet or UV portion of the solar radiation and keeps us protected from this harmful and damaging type of radiation. The atmosphere contains many different gas species. Greenhouse gases, such as water vapor, methane, and carbon dioxide, are transparent to the incoming shortwave radiation, but are opaque to some wavelengths of the long-wave energy from the Earth. Molecules of these gases absorb long-wave energy from the Earth and re-emit less long-wave radiation than they absorb. This traps some of the heat energy in the atmosphere and causes the Earth's temperature to increase. By including an atmosphere with the energy budget of the Earth requires the surface temperature of the Earth to be about 58 degrees Fahrenheit, and humans, animals, and plants are able to live. However, since the early 1900s, concentrations of greenhouse gases, such as carbon dioxide and methane, have risen. We know from the Earth's energy balance that with more molecules of these gases absorbing long-wave energy, the temperature of the Earth's surface and atmosphere must rise in response. Many scientists believe that Venus experienced what's called a runaway greenhouse effect, causing it to become the hottest planet in our solar system, with a surface temperature around 872 degrees Fahrenheit. Early in the history of our sun, Venus may have had a global ocean. As our sun got stronger and its brightness increased, this global ocean began to evaporate, filling the atmosphere with water vapor. Since water vapor is a greenhouse gas, the amount of long-wave radiation trapped in Venus's atmosphere increased, causing the temperature to rise. The hotter temperature eventually led to the ocean boiling away, creating more water vapor. Over time, much of the hydrogen escaped from the atmosphere, leaving the oxygen to chemically recombine with carbon. Venus now has an atmosphere that is 96.5% carbon dioxide. There are many other processes that can impact the energy budget of the Earth. One example is clouds. Clouds can impact the amount of incoming solar radiation that reaches the Earth's surface. Globally, clouds reflect about 24% of incoming radiation, reducing the amount of radiation that the surface receives and cooling the Earth. However, clouds, especially high clouds, also absorb long-wave radiation emitted by the Earth, and this acts to warm the Earth. Understanding this balance between the cooling and warming effects of clouds is very important for future climate change. In addition to the characteristics of the surface, atmospheric composition, and the role of clouds, many other interactions can impact the energy balance of the Earth. Scientists today are working actively to better understand the role of aerosols, fine solid particles like dust and air pollution, in reflecting, scattering, and absorbing energy and heat. Another area of intense study is how changes to land cover and land use through processes like urbanization and agriculture impact the energy budget. Understanding the Earth's energy budget is very important for determining the temperature of the Earth. It can be very complicated if you account for every individual process, but always comes down to the basic balance of incoming shortwave energy and outgoing longwave energy.